propagations. 6. Social networking, finding shortest connections path. Um, we are going to see how this graph move through the vertices. This is a level order travel technique use. We can make this graph into a tree. You can start with any node you like. I will start with a node. When you start with that, it connects to the B and C. I have made the tree by taking A as the root node and BC as the leaf node. Then we go to B, B connected to D and E. But you can see that B is involved in A by now. We can use the node D and E to create a tree for another level. Now if we go to C, C joins A and D. C is currently involved in A and C needs to be connected to D. Then go to the D. D connects to C to B to and E. D already connected to B and it need to be connected to E. E needs to be connected to D and B is already connected to it. We can create a simple tree like this using the graph. So we can call several levels in this tree. A is first level, BC is second level, DE is third level. Now, uh, we can move from level to level in this tree. First, we meet A. So there is no more element in level 1. Then we go to level 2 and going to B and C at level 2. So level 2 is over. We are moving on to level 3. Then go to D in level 3 and then go to E. So this way we can get one result in the first search. Uh, so we can get several answers from this, but this is one answers we got. Examples for breadth uh, finding search. Steps 1, queue and visited array are empty. So visited array is empty and queue also empty. Second step, enqueue into queue, then the first element is dq. So visited array is A, result is A. Step 3, queue is empty. Step 4, after B and C has the adjacency elements of A. So B and C enqueue into Q. Then the first element is DQ. Visited array A, B, C. Result is A, B. Step 5, after explorations B, A and E and D has the adjacency elements of B. Then D and E is unvisited elements, so D and E NQ into Q and the first element is DQ. So visited array is A, B, C, D, E. Result is A, B, C. Step 6, after exploration C, A and D has the adjacency elements of C, but they are visited. So they are not again included Q. Then first element is DQ. So visited array is A, B, C, D, E. Result is A, B, C, D. After explorations D, C, B, and E is adjacency elements of D, but they are visited, so they are not included in Q. Then first element is DQ. Visited array A, B, C, D, E. Result A, B, C, D, E. Step 6, after explorations E has adjacency elements, but there are no unvisited one. So no more elements have been added to the queue. Now queue is empty. Visited array is A, B, C, D, E. Result is A, B, C, D, E. Queue is empty. So now moving to the code part of the breadth first search. Graph class explanations. The graph classes represent an undirected graph using an adjacency list. The adjacency list is an array of linked list objects where each element of the array represent a vertex and store a list of its adjacency vertices. The graph is initialized with the number of vertices. Um, Private integer v. This represents the number of vertices in the graph. Private linked list integer integer list. This is an array of linked list. Each index of array holds linked list represents the neighbor of vertex. Um, a construct um, graph integer v. The constructor initialize the graph the with v vertices. It also initialize an array of linked list object to present the adjacency list method add edges int integer v integer w. This method adds and edges between vertices x and vertices w. The edges is directed, meaning v is added to v adjacency list. Public void add edge in integer v integer w. BFS integer started. This method perform a breadth first search. Traversals is started from a given vertex started. Queue. BFS uses a queue to explore node level by level. Visited array keeps track of whether a vertex has been visited to avoid cycles and revisited node. Initialize visited an array that tracks whether each vertex has been visited. Q for BST, uh, a queue linked list is used to store vertices as they are visited. Started node. The started node is marked as visited and added to the queue. While loop continue until the queue is empty. It dequeues the front vertices, prints it and added it unvisited neighbors to queue. Now we can move to next part, differences between breadth first search and depth first search. This is the diagrams. You can understand and get clearly idea about differences between these two graphs. breadth first search exploration. It explore all the neighbors of a node at the present depth level before moving on to the node at the next depth level. Uh, Depth first search explore. It explore as far as possible along each branch before backtracking to explore other branches. BFST. Breadth first search traverse order level by level. uh, Depth first search, traversal order, deep first, going deeper into the graph before checking the next sibling nodes. Breadth first search, data structure uses a queue to manage the node. Depth first search, data structure user stack. Uh, Breadth first search, time complexity uh, 0 brackets v plus e, where v is the number of vertices and e is the number of edges. Depth first search, time complexity is 0 brackets v plus e, where v is the number of vertices and e is the number of edges. Breadth first search, uh, space complexity 0 brackets v, since it's store all the nodes at the current level. Uh, Depth first search, space complexity 0 brackets v for recursions stacks or the exclip stack. Breadth first search, best for finding the sorted path in an unweighted graph or level-wise explorations. Depth first search, best for exploring all possible paths or searching for a particular conditions. So lesson is finished. Uh, Thank you listening for me. Uh, See you in the next video.